All right, we're in section 10.6 where we're going to find segment lengths in circles. So we have a bunch of different theorems that give us formulas to help us find um, different lengths in circles depending on what information is given to us. So the first one that is shown on the screen is we have the segment of chords theorem. So it states that if chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord equal to the product of the lengths of the segments in another chord, which they give us as EA, which is here, so, and then times it by EB, which is here. So it's the same line segment. You're just multiplying it by the values once it hits that intersected point E. Then we have that's going to be equal to EC, which is right here, times it by the product of ED, which is right there. Again, it's the same line segment. It's just you're trying to figure out um, what those values are from the point that it hits the circle to the point of intersection between those two chords. The second theorem that we have, it's called segment of secants theorem. It says if two segments share the same endpoint on the outside of a circle, which they do here at point E, then the product of the lengths of one side and its external segment equals the product of the lengths of the other secant segment and its external segment. So EA is the external segment in this case, and EB is the entire secant. So that segment of that value from where it touches the circle at the end point to where they share their point on the outside of the circle. And that's going to be equal to EC, which is the line segment on the outside of the circle, and it's going to be times it by the entire line segment. So it's a little bit different in how it was structured when they're inside the circle. It's just going to be, not only is it just the products of what's on the outside, but then it's going to be multiplied by what the entire segment is for those particular problems. Finally, there's a segment of secants and tangents. So this is my tangent. This is my secant here. So what they're stating in this one is as if a secant and a tangent segment share an endpoint on the outside of the circle, then the product of the lengths of the secant segment and its external segments equal the square of the length of the tangent segment. So if you have the tangent segment, which is EA right here, that gets squared, and it's going to equal kind of like how it was with the segment of secant's theorem. It's whatever it is on the outside times it by the entire segment, which is ED in this case. So uh, for these first two examples, we are going to follow the segment of chords theorem. So looking at this for the segment of chords theorem, we could say that 3 and x are going to be products, so the product of those two is going to be 3x. And then the product of these two here are 4 times 6, which is 24. Dividing both of those by 3, I get x equals 8. Looking at the circle to my right, I got the product of these two values, so it's going to be x times it by x plus 4, and it's going to be equal to the product of these two values, which is going to be x plus 2 times by the quantity of x plus 1. On this side of the equal sign, we're going to distribute. When I do that, I get x squared plus 4x. When I go over here, I get x squared plus 3x plus 2. So in this case, the x squareds actually get canceled out. And then from here, I can subtract 3x to both sides. This gets canceled. I'm left with 1x over here. all I have left on the right-hand side is 2. Looking at these two examples here, these two examples fall under the segment of Secant's theorem. So using that formula to help us out. So on the exterior here is I have 6, so I got 6 times it by um, the sum of this entire angle, which is going to be 9 plus 6, which is 15, and that's going to equal the outside here, which is 5, times it by the entire thing, which is going to be x plus 5. So 6 times 15 is 90. And distributing this, I get 5x plus 25. Taking 90, subtracted by 25, I get 65. And so that's 5x, divide that by 5, x equals 13. So again, if you checked it out, you would have 6 times it by 15. That would be equal to 5 times it by 13 plus 5, which would be 18. So 6 times 15 is 90. 5 times 18 is also 90. So it checks out. So that's one way you can check your work. Looking over here on the right hand side, we have 3 on the external, and it's going to be times it by this and this. So like term is going to give me x plus 5. And that's going to be equal to x plus 1 times it by the sum of this. So negative and positive kind of cancel out. So I'm just left with x plus x, which is 2x. So this one here, I get 3x plus 15. That's going to be equal to 2x squared plus 2x. So subtracting 3x, subtracting 15. I just do that because I like to have my lead coefficient to be positive. So 0 equals 2x squared minus x minus 15. Anytime you have a quadratic, which means you have that x squared there, it's going to be, uh, um, we have to have it set equal to 0 in order to solve. So you can solve this one of two ways. Hopefully we can factor it. But if we can't factor it, then we can use zero product property or use the quadratic equation, quadratic formula to help us solve it. But I believe we'll be able to factor this. So 2 is a prime number, so I know it's going to be 2x and x. I know the signs are going to be different, but I can't tell what that which one's going to be plus or going to be minus quite yet. All I know is that the product of these two values plus the product of these two values is going to give me a -1, and these two values here and here are going to give me 15, more specifically -15. So let's see what we can come up with. So I'm guessing probably 3 and 5. So if I put 5 here, that give me 10. 3, that doesn't give me 1. So if I put 5 here and 3 here, this is 6. This is 1. Their differences give me the 1. But this where the minus would be, this is where the plus would be, because this would be -6. This would be the +5. That's where we get the -1 from there. So zero product property tells me that x would equal a -5/2 here. This one would be x would equal +3. Because it's negative, we omit that because we're dealing with measurement. So x would be 3. So x would be 3 in this case. So if we looked up here, this would be like 3 times it by, so if that was 3, so that'd be 5, 5, and 3 is 8. That would then be equal to, so this would be, what, 4, this would be 3, so then it would be 4 times it by, what, 7? No, oh, this would be 2, I'm sorry. This would be 2, which would make it 4 and 6, so 24 equals 24. Okay, and then finish off, this is the secant tangent. So we got our tangent line here, which means that we're going to square 12, and this is going to equal x times it by the quantity. In this case, it'll be x plus 10. So x squared, or 12 squared, I'm sorry, is 144, and this is going to equal to x squared plus 10x. So subtracting 144 to both sides, I got 0 equals x squared plus 10x minus 144. It's a simple trinomial, so I assume we could probably factor this. So I got 0 equals parentheses, parentheses. I got x and x. Different signs. Larger numbers can be attached to the plus sign. Two values that give me a product of 144. Difference is 10 will be 18 and 8. Zero product property will state that x would be negative 18 and x would be positive 8. Because we're dealing with measurement, the only one that works is x is 8. Finally, we have another tangent, which is at 12. So again, this is 12 squared also. And it's going to be equal to 8 times it by the sum of the entire line segment. So combining like terms is going to be 3x plus 9. So 1 plus 8 is 9. So 144 is the square of 12. And then this turns to 24x plus 72. 144 minus 72 in this case is 72. And then divided by 24, x equals 3. And that is being able to find segments, lengths, and circles. Hope this helps. Till next time.